Are you ready? Brilliant. Hello. My name is Mark. You might have seen me on the internet. I'm known as Large Cardinal. I'm more affectionately known as Mark Carney. Same name as the Governor of the Bank of England, just not the salary, I'm afraid. So I'm going to talk to you about a few little bits of hardware. It's what I do for a living. It's what I do for research. When I'm not doing that, I'm doing a PhD at the University of Leeds. So there's lots of maths in my life. I love it. Numbers. Oh, yeah. But most people don't. They see, oh, you do maths. Okay, they leave you alone at the party. It's a great way to sort of get your own personal space. So what I'm going to do is I'm just going to show you some more of the unusual hardware attacks that you tend not to see too much demonstration of, because it tends to be kind of sometimes a bit of a one-shot wonder. You do it in a lab and then you never see a realization of that. Let's talk about this. This is the kind of attack that you see quite a bit, but you won't have seen this one because this is technically a 0-day. Okay, so here's what's happening. This is an STM32F103. Who's heard of these? Anyone not heard of these? Okay, a few people. They're very well known. They're little core ARM32 chips. They're absolutely brilliant, lovely, very cheap, very powerful, very fast. They work really well. However, these are the boot pins. If the debug is disabled, you can kick it into bootloader mode. You can then go into the firmware and patch out these 2 bytes located at this location. And when it goes from 8062 to 0072, when those 2 bits are flipped, then the debug will be re-enabled and you can just push the firmware back up, and now you can debug as if you are running it as a developer. Okay? Very nice, very simple, very easy, not very difficult at all. No one spotted it yet, so here it is on the slide. 0-day. Thank you very much. I'll be here all week. Okay, so I want to talk to you about some more interesting attacks. Okay, some things you don't really see very often. Who's heard of Powerline Analysis and glitching and fault injection? A couple of people. Okay, brilliant. Yes. Right, so we're going to talk about this, about how it can affect a similar thing that we just saw. Okay, so this is an overview of Galinsky's attack on the LPC 1343. It's a very simple attack. The chip itself had 4 modes. It had CRP. Does anyone not know CRP? Code Readout Protection. You can imagine what that's for. It stops people being able to read out the code on your chip. Okay? Now, the values for CRPs levels 1, 2, and 3, and a thing called no ISP, which I won't go into now, were all very well defined. It was like 1, 1, 2, 2, 3, 3, 4, 4, that's CRP level 1, 4, 4, 3, 3, 2, 2, 1, 1, that's CRP level 2, etc., etc. However, if you gave it a weird value or a random value or basically a value that wasn't one of these 4, it was as if there was no protection. That was, there is no protection on this chip. So this is where a glitch, a fault injection, is very useful. If you can time it correctly, get it just at the right moment, okay, then you can actually change the behavior of the chip. So what's a glitch? Well, there's 3 main kinds. There's a voltage fault injection, there's a clock fault injection, and there's an EM fault injection, okay? I call VFI, CFI, and EMFI because we're not very inventive. So we have these different ways of doing it. What we do is we attach to the actual chip, and we manage to sort of swap out. We call it a mini brownout. Okay, the kind of timescales we're talking about, microseconds to nanoseconds. Okay, very, very, very short. What we do is we bring the voltage down sufficiently that then the chip, when we bring the voltage back up, hasn't shut down, it hasn't reset, but it's glitched. Okay, you've seen glitch art, yeah, online. It's the same kind of idea, but here what we're doing is we're actually changing the behavior. So the reset into the application looks like this. With a correctly timed glitch, you can make it look like this and re-enable the bootloader. For those of you who'd like to see more, there's a link to the slides on the bottom. That's the kind of stuff that I like talking about, because this stuff, right, means that, you know, if you're using one of these chips, I will always be able to get the firmware off. Always. Simple power analysis. Okay? Power analysis is where we look at the amount of power that's being used. So, we would start off with, say, taking what's called a shunt resistor over the ground plane, and then you put a little oscilloscope over it. And then you can read the voltage, or not an oscilloscope, just a voltmeter would do, but the voltage then corresponds to the power because V equals I over R. Right? Ohm's law. Okay? So you can get the amount of power by taking that resistance, which you know, and the shunt resistor, and then multiplying it by the voltage, and that gives you the power consumption. Okay? The number of electrons going through the circuit. That then can tell you what it's doing inside. And often you'll see, like these, I think there's some groups at Tel Aviv University that like do this for like a party trick or something, whereby they keep pulling off RSA keys. You've seen some of these research papers? This is what they're doing, okay? What is an RSA key? Who's not heard of RSA? Everyone's heard of RSA. Oh, good. Okay, so RSA is an encryption cipher. It uses keys that are very, very long, but they're using an exponent, okay? So you have a number to the power of the key, and that is how you do your encryption, okay? Exponentiation is a rather difficult process, okay? So what you do is, you use an algorithm, you use a cheat method, and this one is called the square multiply method, okay? Simply put, you read the bits of the exponent. If it is a 0, you do a square. If it is a 1, you do a square, then a multiply. It is perfectly possible to read the power signatures of each operation, and you will be able to read off square, 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 multiply, square, multiply, square, multiply, square, square, multiply. It then doesn't take very much logic to be able to go, the key is obviously 00111101. Okay? When you see these kinds of attacks on RSA, they're usually something like this, because this is how we do it. Okay? And all I'm doing is I'm just listening to the chip very carefully, okay, with an ADC. It's sufficiently fine enough. You need about 100 megasamples a second on each oscilloscope channel to do this properly. That's the kind of granularity that you need. So what I'm going to show you is I'm going to show you a differential power analysis, okay? AKA, can I swear? Does anyone mind if I swear? Bloody magic. Okay? The DPA works like this. It's non-invasive, again. You're not actually changing the structure of the circuit or the chip, okay? You're just adding a shunt resistor, and you're just measuring the power consumption, okay? This was an attack that was come up with a good few years ago now. This is the kind of thing you will see. Who can see the difference here? Spot the difference. Who can see it? Exactly, you can't. Okay, neither can I. But if you have a computer, you'll see there's the difference multiplied by a factor of 15, and you get this out. And what this is showing you is it's showing you the different parts of AES under different levels of power consumption. And with that, there's a statistical process whereby we can take the power line that we see, and we can begin sorting them according to what we think the key is. So we can make a guess, and then we can refine that guess. And the more samples we have, the more capable we are of working out which bits are going where. Okay, don't worry. This is all well written in this paper, okay? And what you do is, you just plug it all in, align the monitoring. So the thing that you don't see in these talks about glitching attacks is about the 17 hours it takes to precisely time when and for how long you glitch, or precisely time where you take your power trace from, okay? And that's kind of the thing that isn't put in because it's not sexy, right? You don't want to see me messing around for 5 hours, in front of you. It doesn't even fit into a lab. You'd just be there going, he's swearing at the computer again. Okay, but what I'm going to do is I'm going to show you a pre-done example with the materials that are required and how simple they are. So this is a chip whisperer. Who's heard of these? Brilliant. Here's one. Okay? This has an open ADC, 10-bit ADC on it, and it will let me talk to chips. I can send UART and other debug control signals out of this connector, and then these two will give me, this is a glitch and this is a measure. Okay? The glitch will let me drop the voltage for a specified amount of time, and the measure will go straight into the ADC and let me read the power. How do you wire it up? Well, that's actually very easy. If you buy the normal chip whisperer, you just get one board. If you buy the level 1 kit, you get one of these, a CW308. Okay? This has a little it's called the UFO board. Okay? Hence the silk screens of aliens everywhere. So, the idea is now all of the inputs are now unified. Okay? What we're doing now is we're able to say, we're going to put the chip on a board with a known pin out. Okay? And it comes with breakout boards. Okay? And we're going to actually wire it up. I'll show you how easy that is, because all you do is you wire this onto here. This is where the shunt resistor is. Okay, this is now giving me the line out. That's going to go over here to the actual measurement side. Okay. If you want to look at the video of this, the link there in the description is actually the video. But simple as this. This is just a ribbon cable, which is all just, everything's predefined. All the pinouts are already done. You don't need to do any actual work here. And then when you do the scripting, everything's really easy. Okay? And the last thing you need to do is plug it in. Okay? Who's seen this before out of interest? Anyone? A couple of people? Okay. So this is not magic. It's actually quite straightforward. So let's plug this in and see how we go. Here we are. And we're in. So now what I need to do is go into my chip whisperer software. I'm going to run software CW, and there's two things here. One is called CW Capture, Okay, it's a very nice little tool. Okay, who's seen this? A couple of people. Good. So now I've just connected to the chip whisperer. You'll see all the lights have started blinking different colors if you were here. Just going to set this up for what I want to do. Okay, it's done. I'm going to set this up to get, we'll try it with 150 samples. That should be enough. So here is the current power analysis, okay? And you can see it's changing a little bit. What it's actually doing, if I show you in the tool, the actual status monitor, this is the key, the text going in, the text coming out, the expected text, because I can give it a key. Okay, so I've given it the key already, because I want to test this on a development system first. So I now am able to simply press go. And you'll see these little wiggles, yeah, little up and down motions. These are the changes in power consumption as the encryption's going on with different inputs. So we know the bits that are going in, we know the bits that are coming out. If you look at the AES algorithm and you look at the way that the S-box works and the way that the various kind of, jugglings of 4x4 byte arrays work, you'll see that you can actually work it backwards. If you just take the time to go through the diagram, you can work out what's going on. Now, you don't actually need to understand all of that to see the actual results, because if I now just save this, and I have another one, a few I made earlier just in case, DPA3 will be fine. We are now done on this side of everything. Everything is done, okay? So now we just take that off, close that up, and now all we need to do is go into the analyzer software. Okay, so now this is a separate piece of software designed for doing the analysis of all these samples. So it's very simple. All I do is I just load a file. Again, you're not seeing the several hours that it takes to actually get this running. Okay, get this running. And what you're seeing here is now doing the statistical analysis. The key I've already given it, so we can identify it, is now finding the correct bits of the key. It's just analyzing the power consumption, and you're able to get whole chunks of the key out, okay? And you'll see more and more of the key will emerge. I have a sample of like 500 samples or 1,000 samples, and you by about 250, you've got the whole thing. So there's a few bytes of the key that have just emerged, okay? It just happened, all right? If you want to see it actually work fully, I'll show you that afterwards, okay? Like I said, a little bit like magic, okay? So what can we do? With security, we don't talk about one thing. We don't talk about the when. We talk a lot about the what. We talk very much about the how, okay? We sometimes concern ourselves with the why, but we very rarely talk about the when of security, okay? We talk a lot more about this. Why do I mention this? Your crypto is broken on your chip. I'm sorry. We will find a way of breaking it, okay? We will find a way of doing it. We understand the mathematics. We understand what is going on. We will break your chip, okay? Put simply, you need to assume that your devices are broken. You need to assume that the secrets on one device are going to be compromised. Okay? In Kirchhoff, Anton Kirchhoff, who was a Dutch, I think, military strategist, in 1883 said a crypto system should be secure even if everything about the system except the key is public knowledge. Known as Kirchhoff's principle. Not to be confused with Kirchhoff's principle of circuits. Okay? That's a common thing that gets done. So, Kirchhoff's principle, it clearly has a lot of value, but what does this relate to things like IoT and hardware? Well, maybe there's a paraphrase we can have for IoT, okay? An IoT system should assure some level of security, okay, even if the complete compromise of one device is assumed. Have per-device secrets. Why do you have one secret across all of your devices? You should have per-device secrets. Yeah? You should be able to discern what is going on, and you should be able to work out how the security of your system is set up without having to worry about anything else. The Enemy Knows the System, Claude Shannon, 1949. Okay? And you've seen just how well we can know the system with a little bit of statistics and a touch of electronic magic. My name is Mark. I'm Large Cardinal. Thank you very much for your time. Any question? Yes?
I assume you break it by giving it a known key, and then go back and run the same process against the unknown key.
Yes. Yes. So what you're seeing there with the red, so the question is, you would do it with a known key first? Yes, of course. So you would hone the attack on the right hardware, on the same hardware, such that you can then put in the target, do a swap, and then you know that you've done your work. Okay, that's the process here. You can buy blank boards for this particular setup. Any other questions? Thank you very much for your time. Cheers.